All right, just a couple of quick things before we move on to the Big Bang itself. Um, all right, it's going to be time for me to come clean about something that it hasn't been quite right. For a while now, we've talked about galaxies having a redshift, right? Because they're moving away from us, and so whenever a source moves away, then you get this Doppler effect, this redshift. Okay, it's time to come clean and say that what we discovered was that, and now you should start to get a little suspicious, this is not really what's going on. Because what we said was galaxies are not really moving through space, but it's space itself that expanded, right? From the early time to the late time. So if galaxies really aren't moving through space that fast, there are little local motions in their clusters. But if the reason why they seem to be moving away from us is because the space is expanding, not because they're rushing through space, then does the Doppler formula really hold? Is it really true? Because they're really not moving through space, right? The space itself is expanding. And that's true. So it turns out, well, what you might worry about is, okay, are the redshifts that we're observing, is that just an illusion? Are there really redshifts? Yes, they're really redshifts. What I haven't told you yet is the reason for the redshift is not the Doppler effect. We tell you it is at first because that's familiar. Everyday objects that move relative to you experience you experience the Doppler effect. That's not what's going on with these galaxies. We just say it is, and then we do calculations, and then I'm going to tell you the real thing, and the real thing is that's not what's happening. But the cool thing is that the math almost works out the same. So you really, a lot of the results don't have to change very much. But the reason is very different. Here's the reason. Okay, it's still true that the distance between, let's say, maybe the distance between that galaxy and that galaxy has definitely increased, right? Here's one and here's one. As the universe expands, the distance between those galaxies in some sense gets larger, even though they stay relatively fixed on the surface of the balloon, right? But the distance between them is increased. Okay, so here's what happened. Let's say, just for the sake of argument, let's suppose in the early universe, suppose light taking off from one to the other it would take 1 billion years to get from one dot to the other dot. Maybe it's an ant crawling on the surface of this large balloon. And so if light is like the ant crawling from one thing to another, the ant says, cool, I can get there in 1 billion years. That's how far away it is. So the ant starts its journey, right? The problem is that in that billion years, now the universe has expanded. And so sure enough, the light has made it that distance in 1 billion years. But the problem is there's been more distance added, right? It's literally moving the goalposts. And so the light hasn't gotten from one thing to the other. Now it's got a lot farther to go. This is the essence of the problem, is that this is how light from the early universe can just now be getting to us, right? It might take, instead of the 1 billion years you might think at the beginning, by the time the universe has expanded, maybe it's going to take light like 8 billion years to get to us. And so when we look in that particular direction, we would see the galaxy as it was 8 billion years ago when the light first went on its journey. And then there's something else that happens too. It's not just that light takes a long time to get to you, but in the meantime, the universe has expanded, right? So part of what, let's say that light starts off as sort of this bluish light, and it's got this wavelength and frequency, right? The metaphor of space being a fabric is actually a really good one. Suppose this really is sort of a thread weaving in and out of a fabric, but then suppose the fabric of the universe is stretchy, which it's a fantastic metaphor. It really works. So what happens is when you stretch the fabric, what happens to the weave in the fabric? It stretches right along with the universe. So what happens is that these galaxies stay fairly still in their own space. And so when they separate from each other, The Doppler effect is not really what's going on. It's not that the galaxies are moving through space. So the Doppler effect does not account for the redshift. What does account for the redshift is the fact that the space stretches. And light, in some sort of real sense, is sort of woven into the fabric of the universe. That metaphor is a really good one. So that over time, if you stretch the fabric, the light gets stretched also. The wavelength gets longer, right? If I pull the fabric with something weaved inside, it gets longer. And so this is the redshift. This is actually called a cosmological redshift. It's just the stretching of the light right along with the universe. The cool thing is that the math works out just about the same. And it also gives us a really neat measure of the universe's expansion. For example, suppose the redshift is, suppose we go from, I don't know, some spectral line normally is at 400 nanometers, and, you know, which is like violet. And then I look at some distant galaxy and I see that line at 800 nanometers, which is like in the infrared, right? So that redshift is 100%. It's gone, the wavelength has gone up by 100%. Well, what that tells me is, the new way of thinking about it, what that tells me is that the universe has stretched from the time the light was emitted, the universe has stretched by 100%. It's doubled in size. Between the time that the light was emitted and when it finally got here, it's been stretched by the universe. It's sort of woven into the fabric of the universe. And so this cosmological redshift directly tells us how much the universe has expanded since the light was emitted. Okay, very cool. So if something has a redshift of 100%, that means the universe has doubled in size since it was emitted. Another way that you can think about it is, how big was the universe when the light was emitted? What you can do is you can take the redshift number, and you can do, if the redshift is 100% or 1, right? Usually we have like fractional, like 0.8, 0.9, 1 would be 100%. What we do is we say it's called the scale factor, which is sort of like the size of the universe. The size of the universe is just 1 over z plus 1. Here's how that works. Suppose z is 0. Suppose there's no redshift, right? If z is 0, then that's 1 over 1. So that's things that are emitted in the present day. If the redshift is 100% or just 1, then the scale factor is 1 over 2. In other words, when the light was emitted, the universe was half as big. Cool. So the redshift directly tells us about the size of the universe when the light was emitted until it got to us. So the redshift is not quite a Doppler shift that we had talked about before. We sort of have to come clean now and tell you what the redshift really is. But what's cool is that it actually is even cooler. It tells us more information about the expanding universe. Okay, neat. Okay, what else is going on? Let's imagine, and this is going to lead us onto the Big Bang. Let's imagine running the clock backwards. If we run the clock backwards from now to early times, what does that mean? That means that the radiation of the universe is getting more compressed. And when you compress the radiation, if you go from red to blue to violet, right, that implies a hotter temperature. That's related to hotter temperatures. So what we sort of hinted at before is that when the universe was younger, it was hotter because everything has been more compressed. So long ago, the universe was smaller and hotter. And we can start running the clock back. How hot could it get? Well, what we know is we have pretty good experiments to tell us what matter and gases and matter are like at hotter and hotter temperatures. So we can imagine what the universe was like long, long ago when everything was compressed to where the universe was, where we're going to kind of pick up the story, is where the temperature is about 3,000 degrees, 3,000 Kelvin. Roughly the temperature of a red star, right? The surface of a red star. Long ago, the universe used to be this, the entire universe used to be this temperature, and this was a redshift of about, 1100. The universe was about 1100 times smaller than it is today. Still pretty large, but 1100 times smaller. So the entire universe glowed like the surface of a star. This is an important temperature, as we'll see. This was about, we can run the clock backwards, knowing the expansion rate of the universe. We can run the clock backwards, and we know this was about 14 billion years ago. How do we know that? Because we know the Hubble constant. We know that H, the thing that's 70 kilometers per second per megaparsec. We've measured that, right, by looking at distant galaxies. And what's neat, what we said was, we said that the speed of a galaxy was the Hubble constant times its distance away, right? The Hubble constant related the speed of a galaxy and the distance. Well, we can do kind of a neat thing. Look at this. Let's do this. Let's move that v over to one side of the equation. What is distance divided by speed? You guys do this all the time. What if we have, what if something is like 120 miles away and you're going on the highway, you go 60 miles per hour. You do this all the time. If something is 120 miles away and every hour you're going 60 miles an hour, how long is it going to take you to get there? This is going to be 2 hours, right? A distance divided by a speed gets you a time, how long it takes to cover that distance if you're going that speed. So that combination of things, d over v, is a time. So if you make d over v, what you have to do is move h over to this side of the equation, and with just a little bit of algebra, you can show that that's 1 over h. So whatever the Hubble constant is, if you just take the inverse of it, 1 over the Hubble constant, that's telling you some kind of a time. In fact, what the Hubble constant is really telling you is how old the universe is, which is neat. So if you take 1 over 70, it turns out you have to account for some unit changes and like multiply by 1,000, whatever. Anyway, it's related to 1 over h. What you get is about 14 billion years. So our measured Hubble constant tells us something about how old the universe is. Now, that assumes that the expansion rate has been constant the whole time, and as we'll talk about next time, it hasn't. But that's a first guess, right? That gets us pretty close. So just by observing the Hubble constant, measuring the Hubble constant, measuring how fast distant galaxies are moving away from us, all we do is we take 1 over the Hubble constant, and that tells us how old the universe is, how long it has been expanding at that rate to get to its present size. And it turns out that's about 14 billion years. Neat. So what happens if we just wind the clock back? What happens if we take this radiation and compress the universe at this rate for 14 billion years? What do we get? We get a temperature of about 3,000 degrees. And something special happens at that temperature, which is something that we'll come back to next time.